Phytoplankton are tiny organisms that live in the ocean. They're everywhere, but they're so microscopic that you can't actually see them with the naked eye. They play a very important role in our ocean's climate. They form the base of the marine food web, so everything else that lives in the ocean eats, to some extent, phytoplankton. But they also play a very important role in regulating climate. They absorb carbon dioxide from the atmosphere and produce oxygen. In fact, about half of the oxygen in the air that we breathe actually comes from phytoplankton. They also help to lock away about 1/3 of atmospheric CO2, so they really do play a fundamental role in regulating climate. So for monitoring phytoplankton, one of the most effective tools that we can use is satellite ocean colour data. Phytoplankton are microscopic, you can't see them with the naked eye, so you might be wondering how on earth we can see them from space, which obviously is very far away. Well, the phytoplankton turn the water a shade of green, and that's due to the chlorophyll in them. That's a pigment that helps them photosynthesize and take up carbon dioxide. With a satellite, we can actually see the colour of the water. That's what ocean colour means. And the key thing about these ocean colour satellites is that they give us global, high-resolution images every single day, something that would be completely impossible with traditional methods like using a ship. So a ship can only travel at a maximum of around 20 kilometres an hour. So to sample the ocean in the same way as we do with a satellite in a single day would be completely impossible. Ocean colour has been around for a little while now, but of course in the old days when they used to look at the colour of the ocean from a ship, it wasn't very informative because you could only see a small patch of the ocean. And it wasn't until ocean colour satellites were launched that people really realised that such a wealth of information could be got from something as simple as the colour of the ocean. By looking at the colour, we look at the green, we look at the blue, and the ratio of those tells us how much phytoplankton there is. The greener the water, the more plants are in it. It kind of makes a logical sense. And so it's a technology which really came into its own with satellites, because before that you just couldn't get the global coverage that you can now. The challenges of working with ocean colour data really stem from the difficulty of extracting that chlorophyll signal from the larger signal. So when the satellite looks down at the ocean surface, it's not just seeing the ocean surface, of course, it's seeing the whole atmosphere between the satellite and the ocean. In terms of ocean colour, the signal that we're interested in is only about 10 to 20% of the total signal that reaches the satellite. So there's obviously challenges there in removing the atmospheric component. Also, ocean colour is not just derived from chlorophyll, the green stuff in the ocean, but also from anything else which adds colour to the ocean. So that might be mud coming from rivers, it could be sediments coming from the bottom of the sea. So there's lots of challenges in using this data. However, we've been working at it now for about 20 years, and we really think we've nailed down getting at the chlorophyll concentration specifically out of that larger signal. Phytoplankton populations are very variable within 1 year and also between subsequent years. Phytoplankton undergo a strong seasonal cycle in the same way that plants on land do. They bloom in the spring, die off in the autumn, and then the following year everything comes back to life again. And phytoplankton, the plants in the ocean, are exactly the same. So we're very interested in understanding what controls when and where that spring bloom happens. It seems to be very key in feeding higher trophic levels, such as fish. So we're very interested in knowing why the spring bloom happens when it does and where. And that basically comes down to the physics of the ocean. This gives us a link into some of the other satellite data that we can obtain from ESA and other space agencies, such as sea surface temperature, wind speed, heat flux. All of these things are considered to be important in controlling when and where phytoplankton bloom. On longer timescales, from year to year, phytoplankton populations also vary a lot, and it seems to be very important for things such as fisheries and for the carbon cycle. One of the things that we're still struggling to understand at the moment, and it's a really exciting field, is exactly what controls those differences. Why 1 year would you have a huge phytoplankton population in a certain region, and in another year there are far fewer? We think it comes down to the physics of the ocean. Again, looking at changes in temperature, changes in mixing of the ocean, and that's where satellite data can again help us. It gives us that large scale view, daily snapshots, which we can't get in any other way, and that's really been at the forefront of helping us to understand these changes. In the near future, ESA will be launching the Sentinel range of satellites, which will ensure the continuity of the ocean colour record for several years to come. This is really important, not only for understanding the impacts of climate change, but also understanding that variability that occurs in phytoplankton populations. One of the things that I think is going to be a next step for ocean colour satellites is the use of hyperspectral satellites. What these do is actually observe the ocean in many more wavelengths than we do currently. This will be able to tell us a little bit about the different species of phytoplankton that exist in the ocean. Right now, all we get is chlorophyll concentration. We don't understand any of the differences between different types of phytoplankton. These new hyperspectral sensors will really be a way forward into that, and it's going to be a very exciting time when they come online. ESA has been instrumental in introducing these essential climate variables, one of which is phytoplankton or ocean colour. And the reason that these essential climate variables are so useful is that they provide key indicators of how the ocean, the atmosphere and the rest of planet Earth is changing in response to climate change. The reason that phytoplankton has been, or ocean colour, has been chosen as one of these essential climate variables is of its very important role in a couple of different aspects of our planet. One is that it's the base of the marine food web, so everything else that lives in the ocean ultimately feeds on phytoplankton, and that includes our fisheries. The other reason is of its key role in the global carbon cycle. Phytoplankton take up carbon dioxide from the atmosphere and in return release oxygen. Some of that carbon that they take up actually sinks down into the deep ocean, and once it's there in the deep ocean, it doesn't reappear for about 1,000 years, so it's completely locked away from the atmosphere. And that helps to regulate our carbon cycle.